So we'll move on to the last, yes, we need to worry you up. We'll move on to the last talk of this session, which is on further tackling correspondence problem and proof generation. And the talk is given by Akihiro Omori.
Thank you for thank you for having me here. In this talk, thank you. In this talk, I'm going to present on further tackling post-correspondence problem and proof generation. Let me maximize the window. Okay. And this work has been carried out by myself, Akihiro Omori, and my supervisor, Yasuhiko Minamide, both from Institute of Science, Tokyo. Let's start by revisiting the post-correspondence problem, or PCP for short. This problem was proposed in 1946 by Emil Post and is well known for its undecidability. The problem is you were given nest types of tiles. In this example, you were given 3 types of tiles. And is it possible to arrange these tiles in such a way that the top string exactly matches with the bottom one? And in this example, one solution is 0 to 0, 0 to 1, 1. And this is a 0-indexed tile indices. And if you arrange these tiles in this order, you can read the top string 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. And the bottom string 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. So you should notice these two are identical, right? So this is a solution, and the answer to this problem is yes, there is a solution. Our study includes formalizing PCP and more in Isabelle Hall. Defining PCP itself is straightforward. Alphabet consists of 0 and 1. Tile is a pair of strings. And PCP instance is a list of tiles. And list of tile indices is a solution if the concatenated top strings is equals to the concatenated bottom strings. Yeah, and so on. PCP SW refers to some subgroup of PCP instances which have exactly S types of tiles, and the length of the longest string on tiles is W. For example, the above 2 instances belong to PCP'25, but the below 2 instances does not, because the right bottom one has 4 types of tiles, right? So this belongs to PCP'44, and the left bottom one has a word consisting of 5 characters, so this belongs to PCP'25. And in this study, we aim to solve all problems in PCP'34. Let me review current situation about PCP'34. There are about 13 million instances in PCP'34 after some normalization. And 20 years ago, in 2003, Zhao solved almost all of them. And 3,170 problems remained unsolved. And several studies solving PCP instances heuristically were conducted after his study, but this is the most comprehensive one so far. In our study, solving all of the remaining problems is the main purpose. But why focus on PCP'34? PCP instances with 2 tiles is shown to be decidable. And the PCP'33, PCP'31, 32, 33 was completely solved in his study. So now PCP'34 is the minimum unsolved problem set. And tackling specific instances might help us to get some intuition about the decidability of PCP instances with 3 tiles, right? That's the motivation. These are our contributions. We solved all PCP'34 instances except for only 2. So now the figure I showed earlier has changes. I solved 3,168 instances in total, but we still have to unresolved problems. And I listed these two here. And you can access my website through this QR code and try solving them yourself. And to solve instances, we've developed two novel methods. And I will talk about it later. Lastly, we automatically generated proofs for each instance and verified the correctness of our results. Why does this matter? We've solved 3,168 instances in total using some thousands of lines of code I implemented. And every time I touch the code, I find a new bugs. So when some ask me, are there any bugs in your program, I can't deny that possibility at all. So to resolve this challenge, there are several possible approaches. The first one is to prove the program correctness. And by proving the program correctness, we can ensure the correctness of the output of the program. But we chose another one, which is to generate proofs that can be automatically verified. I mean, we generated 3,168 proofs, separate proofs, and verified those correctness using Isabelle Hall. From the next slide, I will briefly explain how we proved. Proving there is a solution is quite simple. Here, let's revisit the example I showed earlier. I showed an actual solution to this instance either. So how do you formally prove that there is a solution for this instance? So you already know an actual solution to this instance, so you can provide it as an evidence to show this instance indeed has a solution. This can be achieved with a few tactics in Isabelle Hall. On the other hand, proving there is no solution is much harder. To achieve this, we use an inductive invariant as an evidence. I mean, in other words, the existence of this object, inductive invariant, indicates that there is no solution to this instance. Our method automatically finds such an inductive invariant. From the next slide, I will introduce two methods we employed. Before that, let me explain what a transition system of PCP instance is. Considering the transition arranging tiles one by one from left to right, we can define a transition system. In this example, the first tile is arranged, and now the bottom word matches with the first character of the upper tile. So as a result, 0, 1 remains on upper side, right? So we denote this state as upper 0, 1. And by applying the tile, the upper word becomes 0, 1, 1 by concatenating the 1 to the remained 0, 1. And 0, 1, 1 matches with the first three characters of the bottom word. And as a result, lower 1 is the resulting state. In this way, we can define a transition function T, and the state set is pairs of upper or lower and a word on alphabet 0 and 1. Initial states is the states corresponding to arranging exactly one tile, and bad states is the states having empty word. So now the solvability of PCP instance is equivalent to the reachability from the initial state to the bad states. This is an illustration of a transition system of the above PCP instance. This is the only initial state of this transition system. And by applying the third tile, it transitions to upper 1, and so on. By following the red transitions, you can see the initial state can reach the bad state. So this instance has a solution. Here, the most important concept is inductive invariant. This is the name of some state set satisfying these three conditions. First, it closed under transition. Second, it subsumes all initial states. Third, it doesn't contain any bad states. If such state set exists, we can say that there is no solution to this instance. Here is an example. Let's prove this simple PCP instance consisting of only one tile doesn't have any solution. Obviously, this doesn't have any solution. The initial state is upper 3 ones, and by applying the tile, it transitions to upper 6 ones, then 9 ones, and 12 ones, and so on. Apparently, the reachable states is the pairs of upper and repetition of 3 ones. Reachable states is an example of inductive invariant because it subsumes initial states and is, of course, closed under transition because this is a reachable state and doesn't have any empty word, right? But generally, inductive invariant is not unique, so we can consider another inductive invariant noted here. Yeah, there are several inductive invariant generally. To find such an inductive invariant, actually many methods are proposed for this type of problem. We tried to apply PDR and abstract regular model checking, which is a method to solve regular model checking problem. And we tried termination checker and time rewriting system. And those methods made some success, but our methods overperformed others, so we introduced our methods. There are 2 types of methods. The first one is infix prefix suffix method. This is a method finding a specific type of pattern that every reachable state follows. And in this method, we use a language class infix prefix suffix language to abstract state space. And we have a variant regular language method. This is a generalized version, and it leverages regular language to abstract state space. Let's begin with the first one. To get an intuition, let's observe this case. Lower 011 is the only initial state. And by applying third tile, it transitions to 001100. And please remember 0110 appears here. And disappears now, and appears again. Our intuition says 0110 will never be removed. And if this is correct, the initial state cannot reach bad state, because bad state is a state of empty word, right? To show that, let's consider the state set of words containing 0110 as a substring. We used regular expression here, dot star 0110 dot star. And we can consider applying tile to this state set. The first possibility is the case that the upper word of the applied tile matches with the part of wildcard. In this case, 0110 doesn't match with anything and remains there as it is. And the second case is that the wildcard part is actually empty, and the upper word of the second tile matches with the first character of 0110. In this case, 110 will be the prefix, and the lower word 11 will be the suffix. So it transitions to lower 110.11. In this way, we can transition a state set to several state sets. In this case, eventually it reaches the below state, and as it contains 0110 as a substring, it is subsumed by the root node. So the union of these states is closed under transition. And we call this type of language infix language, and we call this type of language prefix suffix language. We use these 2 languages to abstract states. To find such a pattern automatically, we use some kind of exhaustive search. The difference from the naive exploration is every time we make a new node, we abstract it by choosing arbitrary substring within it. In this case, we chose 1 and made an abstraction node. dot stir, 1 dot stir. And we repeatedly attempt to abstract and transition. And if it fails, backtrack and continue exploring until we find an invariant. Yeah, this is the infix prefix suffix method. And we have a variant called regular language method. In this method, we represent the state as an automaton. And to abstract a node, we merge the nodes of NFA, the automaton. In this example, we make a straight line automaton corresponding to the root node. And by merging several nodes, in this example, by merging Q1 and Q3, we can make an abstracted node. And to implement transition operation, node automata, we can use a combination of concatenation and left quotient operation. For example, considering apply this tile to the root node. Since this is the lower state, we first concatenate the lower word 1, 1 to the language of the language LA. And then we need to consume the upper word 0 from left side. And we can express the language like this. Okay, using these two methods, infix prefix suffix method and regular language method, we could solve almost all problems automatically. But to tackle instances we couldn't solve automatically, we made a manual invariant discovery tool. By using this, you can find an invariant manually. And users can input arbitrary regular expressions here, and this tool is continuously checking the invariant 3 conditions and tells us and counter an example to the closeness. And the user can block the counter example by adding new regular expressions. For example, this is an example I showed earlier. Users can, 111 plus is an inductive invariant. Yeah, congratulations. And please solve and resolve the 2 problems. OK, so anyway, not depending on the method you use, we get a closed graph which looks like this. Specifically, which is a set of state sets, B1, B2, Bn, and the transition inclusion relations, which is, for example, the past state of B1 is subsumed by the B1 and B2 and B3 or something like that. And given this graph, we need to generate a proof which proves the 3 invariant conditions, and there is no solution to the PCP instance. First, we need to define nodes, then prove relations, then merge the relations to show the closedness and other 2 conditions. Let's start with defining nodes. This is an actually generated definition of an NFA for some regular language. You don't need to read this code. And it just defines a transition function. And by using it, it defines an automaton. We faced 2 design choices here. The first was about the type of automata to use, NFA or DFA. And we decided to use NFA because implementing union and concatenate operation on DFA is inefficient and is difficult. The second choice concerned how to represent state of NFA. Initially, we attempted to define a new data type for each NFA, but it internally generate n-squared lemmas to distinguish between constructors, right? So, and at most, NFA contains hundreds of states, so it costs prohibitively. finally, we chose to use binary representation of natural numbers. And as you can see, it has only 3 constructors, and you can easily distinguish between values by comparing digit by digit. Okay, so the config, this is the state, is a pair of upper or lower and the word on an alphabet. And we can define a node using the defined automaton. Okay, we successfully defined the nodes. Then let's prove inclusion relations. Here, all vertices were given as NFAs. And we need to prove a lemma like post state of B1 is subsumed by the union of other nodes or something like that. To do this, we need to implement union operation. And this is easily done because we decided to use NFA. And we need to implement transition function on NFA. And as I mentioned earlier, this is realized by the combination of concatenation and left quotient operation. And both of these two can easily be implemented because we decided to use NFA. The hard part is the procedure of inclusion checking between NFAs. To do this, we used anti-chain algorithm. This is essentially on-the-fly DFA construction. But we didn't want to prove its termination property, so we didn't. What we did is defining step function of this algorithm and proved some invariant holes when stepping the algorithm. And the actual computation is done by transforming a subgoal. This function, this state invariant function, is immediately simplified to true when the algorithm terminates. Okay, so we proved inclusion relations. Finally, we need to match those relations to show the closedness and other 2 conditions. Closedness is proved by combining inclusion relations. The second one is proven by checking acceptance for each element of I. You can do this because initial state is always finite set. The third property is proven by checking acceptance of epsilon for each of automata. Using those lemmas, we proved the existence of an inductive invariant. Finally, using the manually proven lemma, which states there is no assertion if an invariant exists, what a clear name of lemma. And we can show that there is no solution by combining the existence of inductive invariant. We implemented algorithms and proof generators in Rust language. And some proofs were too large to build due to timeout or out of memory. Please note that this doesn't mean we still have unverified instance, because we assume an instance is, the result of instance is verified when one of 2 equivalent instances, original or reversed one, is verified. Reversed instance is just a reversal of the original instance. And considering arranging tiles backward, you can easily see these 2 instances are equivalent. Okay, in conclusion, we proposed novel algorithms and solved all PCP'25 instances except for 2. And we verified those results formally. As for future work, first we need the remaining 2 problems. We need to solve the remaining 2 problems. Second, our algorithm was applied only for the problems which is unresolved in Zhao's study. So we need to formalize his result. And once we successfully resolve all instances in PCP'25 and verified those correctness, we'd like to prove such a lemma, such a wrapping up lemma. This states every instance of PCP'25 is unsolvable, or the shortest solution has at most 452 tiles. And it suggests that we really solved all instances. So we'd like to prove such a cool lemma. Okay, this concludes my presentation. Thank you for your attention.
Thank you. So are there any questions? Claire.
Thank you for the talk. Sorry, I forgot my question. Yeah,
Which slide?
yeah.
On here.
Yeah, I got it.
This one?
So
Okay.
in your benchmark, in your the graph things, in your implementation, why does the reversal change the runtime?
Reversal.
Yeah,
The
tile
reversed instance.
reversal.
So your question is the
Yeah.
transition system of reversed instance is different from the original one.
Yeah, why the runtime is different, or memory consumption is different in terms of the when you reverse the tiles?
Yeah.
Is there any like suspected reason of that?
Actually, I can't find any reason, but actually the original and the reversed instance has completely different transition system, but these two are equivalent. So yeah, I feel this is interesting. Is that the
Okay.
okay? Sorry.
Hi. I wonder, in this checking of the proofs, you are using everything you run Isabelle build. So you're not generating externally code and then run it natively in a language. So to which extent do you use the eval method within your proof scripts? Or could you somehow use some verified automata library which then runs more efficiently than running proof scripts within Isabelle?
So your question is why I didn't use such an existing automata library or something? No.
Not why you didn't use it, but would it be feasible to use it? And to which extent do you use the code by eval method, so to use reflection and run generated code for proofs?
So yeah, we could generate an executable code. Yeah, actually, but we didn't because we would have likely to the fact in the Isabelle whole world. So so if I generate some executable code outside of from Isabelle whole using Isabelle whole code generators, we can of course we can check the some correctness of the certificates, but we'd like to have the correctness. We'd like to show the correctness within the Isabelle whole. So is that understandable?
Perhaps we discuss offline then.
Okay, sorry.
Do you have any theoretical results on like the completeness of this method? So like you're using inductive invariants, like are there any guarantees that you will be able to find all of the solutions eventually if you were to just enumerate all possible invariants that are regular language?
We don't have. If this method has such a completeness, it means we solved the undecidability problem of PCP instances with 3 tiles.
It could still be semi-decidable. Like there are an infinite number of invariants, and
semi-decidable. Yeah. So our method is to show unsolvability, right? So and PCP instances with 3 tiles is the decidability. No, PCP instance with 3 tiles is an open problem, and no one knows our method is complete or not. So yeah, we can say we can't say such a thing.
Thank you. I had one more question, maybe. So, I mean, you've solved this problem with this particular technique for PCP'25, but I'm wondering how the same kind of approach does it apply to these other classes you have there? Does it, and in some sense, does it scale, or is it universal in that sense?
PCP for 3 or other kinds of classes. Yeah, of course, this will be scalable and is applicable to such kind of other classes, but I haven't applied comprehensively yet.
Okay. All right. Well, let's thank the speaker.